All right, everyone, let's get started. Welcome to another CAN seminar. For the CAN seminar series, actually, we are privileged. We're very happy to have a couple of our own people, alumni here, coming back to us from Dinah Test Company to give us today's CAN seminar, and actually a little bit of their background. Kurt Kiefer, as well as Phil Donovan, listed here on the presentation. Kurt will give the presentation, but they're both our students, as I said, and interestingly, again, they're PhDs from us. Kurt was in the very first class that I was teaching in 310, Introduction to Transportation Engineering. It was ages ago, it was, I think. A couple years ago. And then Phil was, of course, doing PhD with me, but Kurt also worked with Professor Sam Carpenter in his PhDs from Sam Carpenter. So now they're heading this top company in this field, actually. Dinah Test has been in business for a long time, but this is a great time for them because they're, I think, in a reorganization, and they're also in the process of hiring new employees, so it's time for you to talk to them. And then the growing business, business especially in the U.S. The way they're setting up their offices and the way they're having new plans to manufacture and actually doing things in a faster and better way, like with the use of FASTFWD that you will be hearing today. So this is all exciting times, and that's why we thought it would be great to hear from them about all these developments. So with that, George.
Well, thank you very much, Earl. It's a wonderful introduction. I appreciate it. It was 1996, 96, yeah, okay, so a few years ago. So thank you guys for inviting us down to give this presentation. It's really great to be back on campus. It's always too long in between visits. However, ironically enough, I was just down here, 3 weeks ago, I think, for the recruiting session that was going on. So it's good to be back in town. And today's presentation, this is very informal. What we're presenting here today is very early stage results from some testing that wasn't really intentional the way we started doing this. It was part of the evolution of a new piece of equipment, and it just kind of, we started observing a few things, and we were surprised by what we were seeing, and that led to some other questions, and we're still exploring everything right now. So what you're going to see here is by no means the end of anything. It's very early stage, very much the early stages of investigation. So like Earl mentioned, the FASTFWD is the focus of the presentation, and how that could be used for accelerated pavement testing. Is there a potential role for the FWD now, given the fact that we can test very, very rapidly to get some information out of the systems that we haven't been able to do so in the past? I should mention the FASTFWD is out in the parking lot, so we're going to go through this a half hour, 40 minutes or so, and then we'll head over into the parking lot, and Phil and I are going to roll up our sleeves and get the thing working, and it'll go fast. So, bad, sorry. Okay, so anyway, the outline of the presentation, what we're going to be talking about today is first accelerated pavement testing. I know that we have an APT device down here. The Atlas machine is at the university, and it's been used quite a bit. Dinah Test, aside from the FASTFWD, we also manufacture heavy vehicle simulators, and we have 18 of these globally that are being used in different countries. We have several in the United States and several overseas. Our most recent, we delivered one to the Federal Aviation Administration that simulates a 736 landing gear, and so we have that. It's over in Atlantic City right now, and we delivered one. The most recent one was over to Saudi Arabia. I think they just got one there, and Korea not so long before that. So we'll talk about APT testing, then the falling weight deflectometer, the original type of FWD, and that's the history of that with Dinah Test, and then the FASTFWD. Really, the FASTFWD is the first serious innovation or advancement with FWD testing in the past 35, 40 years, okay? At least for Dinah Test, all right? It's pretty much been the same product for a long, long time. In fact, I used, HWD, or heavyweight deflectometer. I borrowed one from Soil SME up in Michigan. Number 2, HWD number 2 is still in service. So I couldn't believe it. And that's probably like 35 years for that vehicle. It's still being used. So things don't change much, but now something has, so it's kind of exciting. The inspiration through observation, we're doing some tests to make sure the FASTF didn't blow up. We noticed that it was doing some cool stuff to the pavement, so we started doing some analysis, and that's what's led to this presentation. And then we'll have some results, some very preliminary results, not rocket science, but more to spark some questions, ideas, possible research topics, and then wrap up out in the field. So Dinah Test history, we go back to 76, founded, well, the company started in Denmark, but it was also started by a Danish guy by the name of Anders Sorensen, and I'm drawing a blank on his name, he just passed away, Richard Stubbsted. Stubbsted was doing, those two guys founded the company. Richard came over to California and started Dinah Test USA back in 78. I think we became incorporated. But it was selling, manufacturing and selling falling weight deflectometers, okay? That's where the company started. So it's been around a long time. And then it moved into different product lines and everything, but it really, the company is based on non-destructive testing of pavements. We are now global, and FWDs are on every continent around the world. We have offices now we just opened up an office in Colombia, Peru, Chile, North America. We have several offices. We're consolidating our production to Atlanta, just north of Atlanta and Alpharetta. We have offices in Denmark, now in France, Italy. We have agents that actually sell equipment for us around the globe. The focus of the talk, very basic stuff here. I know you're all masters, PhD students, professors, gazillion years of experience, but Dinah Test is interested in measuring pavement response, okay, both structural and functional, okay? So structural response, we're measuring deflections, strains, calculating stresses. We're doing that with our falling weight deflectometers and our heavy vehicle simulators. We can get that type of structural information out of those devices. For roadway pavements, falling weight deflectometers. For airfield pavements, bigger structures, heavyweight deflectometers. Same thing, just bigger forces are applied for airfield pavements. We also, Errol, you got to play with the lightweight deflectometer, the LWD that we had. Yeah, got to mess around with that. So we're measuring pavement responses, and then we're correlating the response to performance, cracking, rutting, roughness, all that great stuff. So from a functional perspective, if we're just looking at the surface of the pavement, we also test for friction properties. We have friction equipment. We're also testing rutting, longitudinal or transverse profile, as well as longitudinal profile, IRI, roughness, that type of data. So the FWD, again, we're measuring structural performance, which eventually leads to functional performance issues as well. APT, okay? APT historically has been performed using these big devices, these heavy vehicle simulators or Atlas machines. They're MLS, they produce these machines all over the place. They have different ways of testing pavements, full-scale testing of pavements. These are expensive devices, okay? These are operated, Caltrans has a couple of these, Florida DOT has one, Waterways Experiment Station down in Vicksburg has one. These are $2 million plus systems. The one over at the FAA now is a $5.3 million device. I think these are very big investments, okay? So doing accelerated pavement, it's not just buying the equipment, you then have to have a program, you've got to hire people to build test sections, you've got to get funding for all this stuff, and you put this big trailer on top of the pavement and run a wheel back and forth. And then you can control the lateral drift so you get some wander with the testing. You can change the load. You can measure, then put a profiler on the surface of the pavement, measure permanent deformations, things like that. But while you're doing the testing, you can also go out there with a falling weight deflectometer, drop a load on that, measure deflection, see how the deflections are changing over time, calculate the layer stiffnesses as you're doing the testing. You can also be measuring deflections using multi-depth deflection sensors. You can be measuring this in situ during the testing as well, okay? So this is a very expensive investment, okay? And so trying to get a program off the ground, we've sold 18 of these globally, but I think we've only got, less than half of them have real vibrant programs. It's you get someone in there who spearheads the charge, they get the equipment, but then sustaining that over time, it's very sensitive to funding and having the right staff to do this and to keep a program like that alive. So anyway, big investment, not everyone can afford this type of thing. We've tossed around the idea in Dinah Tests of building one of our own so we could, drive it around and test roads and stuff like that. But it's expensive for us too. I mean, it's still, $1 million in cost to build one of these things for the company, or if you're selling it for 1.6 or whatever, it's a kind of a non-starter. So here's how you use the thing. It's got a wheel that goes back and forth, measures deflections, everything like that. You're probably all familiar with this. Why are we interested in doing this? Why are we doing all this testing? If we look at, I like this plot here. This is one of the few graphs that I like to show up here. If we look at initial deflections when we do testing on a pavement, okay, so x-axis, number of load repetitions. How many times easel has been put across, or one load repetition, okay? So we're starting off at 0, going up to 2 million load repetitions, okay? If we look at the elastic deflections under 9 kips of force over at different times after the pavement has been subjected to those loads, you can see that D naught, initial deflection, increases to about 320% of D naught. Around in this test, it was about 650,000 repetitions. Okay, there was no observable distress on the pavement surface. Okay, so no cracking, none of that. If you looked at the pavement, if you were just doing a visual assessment of the pavement, it looks fine. Everything, it's perfect. What are you worried about? Nothing to see there. However, if you go all the way out here to 1.9 million repetitions or whatever, that's where the first crack is seen. Okay, but the deflections have gone from 320% D naught to 410% D naught. So there's not that much increase in the deflections. However, you're putting on a whole bunch more load repetitions. Okay, so what is that saying? Where's most of the damage to the pavement occurring? Well, structurally, it's occurring within this area up here, but then it's kind of hovering in okay shape through here. But right here is where you're seeing that initial increase in damage, and then things kind of even out a little bit. So what the philosophy or the method that Dinah Tests and we're not the only ones that think this way, but if you can get out there and get a sense for the structure of the pavement at the time of construction, measure the stiffness of the pavement when you put it down, and then track that over time, you can get a truly proactive, or you can implement a more proactive rehabilitation strategy because you have a better estimate of when the pavement will actually be failing, much sooner than the time when you start seeing cracking. Okay, so you can start tracking deterioration and damage very early in the pavement's life. So again, you can't bring an HVS out there to test every single pavement, so what can we do with a falling weight deflectometer? Well, here's the traditional Dinah Test FWD. The setup is very, very simple. You have a mass back here, a bunch of weights. You guys will see these out in the field. They're just these little gray slabs. You can put as many weights on there as you can fit on there without messing up the machine. But put them on the back. We raise the weights up in the air. We drop them. Okay, they come down. There's a load plate on the pavement surface. The weights bounce off of some buffers that transmit the load into the plate, and then from that, what are we going to measure? We have these little sensors on the ground. Does anybody know what those little sensors are? It's not one type of sensor, but there are a couple different types of sensors that FWDs use. Geophones. Okay, what do geophones measure? What are geophones measuring? Yeah, not deflections. We get deflections from them, huh? You're integrating two deflections. You're integrating from what to get to position? Velocity. What's before velocity? We're measuring acceleration. Integrate acceleration, get velocity, exactly. And then you get position, right? So we're measuring the accelerations. Some of these devices actually do measure velocity. And some of them measure, not Dinah Tests, but some other manufacturers will measure deflection directly. They'll measure position off of those. But we don't do that. So this is our setup here, and we're just measuring that information. And then from that, there are a gazillion different ways to calculate what each layer stiffness is underneath there. Okay, you measure deflections, and then you can apply different models to figure out what each layer stiffness value is. In order to do this, it's good to know not only the deflections, but also what about the pavement in order to do back calculation. You guys have all done this, right? By hand? No? No? Okay. You need two No, you put together, you want to know the pavement layer thicknesses as well. So you do some coring, and that's why GPR is becoming all popular now and everything, because in order to get a good indication of what those layer stiffnesses are, you want to know the layer thicknesses, and it's expensive and dangerous to do coring all the time. So they're new, a lot of technology goes into finding out how stiff each layer is. These are the old systems. We have our trailer mounted FWD here. Again, we manufacture these assemblies in Denmark, so you'll see a lot of European license plates on these things. But we also, these you hook on, you'll see something that looks similar to this out in the parking lot. But since backing up a trailer causes jackknifing issues and all that, and not a lot of people can do it well, myself included, we also put these in trucks so you can move them around a lot more movable. Okay, so these are the traditional ones, and these were hydraulic systems. Okay, these are very, very different than the FASTFWD, which we'll get to in a second. But you see, this is a traditional heavyweight deflectometer. We have a huge hydraulic system, and this is for testing airfield pavements, a big hydraulic system to lift the big load package up in the back that we drop. Okay, I think this is out in Colorado. Isn't this Denver? Might be Denver. Yeah, a lot of hydraulics back there. Hydraulics are always fun to work on when something goes wrong in the field. You got oil spilling all over the place and people are screaming at you. It's always a nightmare. But the FASTFWD, we've gotten rid of the entire hydraulic system. Okay, there are no more hydraulics with the latest falling weight deflectometer. It's an electrical. It's a linear motor. It's 100% electrical. You can run them off a second alternator on a van, or you can run them off a generator. We have both hooked up out there. We'll run them off the alternator. It's kind of cool. Super quiet.
Do you run a drive screw?
Yes, it's exactly what it is. And good thing we patented that. So we have a DMI. Believe it or not, we're controlling the height of the load package with a DMI that's rotated horizontally. And so we're controlling the height of the drive screw with a DMI that's measuring rotations of the drive screw. And we know exactly where the load package is. And so we get extremely precise measurements of where that is. It operates like a robot. It's incredibly accurate with that. So this comes up, there's a drive screw in here, and then we bring it up and we release it. Okay? I really want us to get to the point where we can drive it. So we're actually, getting more than gravity pulling down on that. But if we could drive that and then control the load pulse with the driving force down, that's next year. But right now we just let it go. And so we have this setup is really nice. It's very quiet. But again, this is a Dinah test. We're a bunch of kind of nerds. We sit around and we come up with these ideas, and we create this stuff, and we're like, oh, wouldn't it be great to be able to test really fast? And we build something, and then we're like, oh wait, we should probably test this a little bit. So our equipment developers give us like a prototype, something to take out into the field and just start playing with. So that's what the consulting division does. So Dinah Test, we have the equipment division and the consulting division. The consulting division is 90% consulting, 10% guinea pig. Okay, so we get this equipment and then we go out and we start tinkering with it. So what you're seeing here, this was what we showed in January at TRB. We had this at TRB, and we're going to have this guy back out there again along with some other stuff this year. But we've since done some modifications to the cooling system, to the protection of all of this stuff. You find things that just don't work quite right, and so we're constantly evolving the system while we're doing consulting projects. So you're wearing two hats out in the field. One, you're trying to get information to your clients. The other, it's like, okay, guys, we really have to do this better, okay, or this needs to be improved. So this is the new, the FASTFWD. The load, it's 1,500 pounds up to 2,700 pounds or 27,000 pounds. What do you guys think after we're done with the FASTFWD? What do you think our next product will be? It's no secret. FASTHWD, thank you very much, exactly. So that's, put 2 and 2 together. That's the next thing that we're going to be coming out with, and we already have the designs for that. This little screw right there, we're finding that heavier loads, that screw likes to snap. It doesn't work quite right. So we're looking at re-engineering this whole thing a little bit. So that'll be out in a year or so, hopefully. Speed. Oh yeah, speed. The speed is almost a non-issue now. We got it. It works really, really fast. I mean, we're 75% more test points per hour in testing. I was out 4 days doing testing myself up outside of Cook County. We have a project with Cook County and the village of Schaumburg, where I grew up. They hired us to do some structural testing up there. I mean, this isn't, from an operator point of view, F1, start, and it ends. Just you push buttons all day long. You drive around and try not to get hit by traffic. But it's super fast. And one of the nice features about this is when you are doing testing out in an urban environment or even on a highway, we've been hit lots of times while we're out testing. So we have chase vehicles out there. One of the big things when you're doing this type of testing is how much time you're out there doing testing. So you want to limit the amount of, basically any disruption to traffic, you want to limit that. So you want to be on and off the road as quickly as possible, not just so you don't get hit, but so traffic or somebody doesn't drive into you or whatever. So this, we're looking on the roadway side, being able to collect the same amount of data in a significantly shorter period of time. Conversely, if we want to get more resolution in data, or if we want to get a lot more testing done, we can do that in a shorter period of time as well. So there's some safety aspects to this thing which are kind of nice. I don't want to go into this one. These ratios are confusing as all. It's our marketing people put that together. Anyway, it's faster. Okay, so I don't know how to present data. Anyway, so here's the sub-assembly for the FASTFWD. So this is the screw and then the weight package, and we have these little locks that come out here, and you'll see all this stuff up close. We'll even let you guys, whoever wants to operate it, we'll let you push the button and start stuff. But it looks very similar to the original, to this FWD. You can see though that we had the hydraulic system running through here, and on either side here we had a support. Now we just have one centerpiece here running through here. All of these fins up here and everything, that's to cool this electric motor that's up top. And this thing gets hot. This gets really, 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 really hot. Okay? And that's one of the things we're still doing is field testing this to make sure that it doesn't like blow up or melt down out in the field. When you take this to Arizona on a summer day or something, you're testing out there, it can be a bit of an issue. Okay? So we have a little umbrella that we put over it to keep it nice and cool, and a little fan, So, so anyway, here's what happened. I said the consulting division were guinea pigs, okay? So part of when we get a new product and we like draw it all up, we get it built, then we bring it out in the field and we start beating away on it. This guy, we took the FASTFWD and we literally strapped it down. Like we started testing. First, we didn't have it tied down. We just put it on the ground and we're like, okay, we wanted to get 1 million repetitions on the thing so that we knew if we could get 1 million repetitions without it blowing up, like, okay, that's pretty good. Then we'll release it. Oh, we strapped it, well, we put it down, we started bouncing the thing. It was bouncing all over the place. The carriage was just like, we couldn't keep it in one position. So we had to tie the whole thing down. And we started testing the same area, that same little piece of asphalt. We didn't even know what we had it on. We didn't start this off as a testing, like a pavement testing project. It was an equipment testing project. But we noticed that, we're getting these deflections and deformations under the load plate. Like, what the heck is going on? And we start seeing, and we're like, maybe we should measure these things. So we start going out. We got a little rig with a profile, a laser profile, and we started doing some measurements. We're like, wow, we're actually, watching the pavement deform. We're getting deformations out of this thing. It's happening really, really quickly. It's just going boom, 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 like all day long. And the first prototype, the first time that we were testing this, that little motor up top kept smoking, and it would start like, so we had to stop every 100 drops, I think. We had to stop. and like blow on it a little bit and then start testing again. And so we did that, and while that's going on, we start measuring some deformations. And then some of you guys may know Per Ulitz over in Denmark. Okay, so Per, he's working with us still. He does a lot of he helped us develop California ME, the mechanistic empirical California's version of the mechanistic empirical design guide. He's been working with us still, and he came over and he's looking at this. He's like, wow, hey, this is kind of cool. Let me apply some. He doesn't talk like that, but he comes over and he's making observations, writing things down, and then he goes back home and he starts doing some modeling with the data, and he has the technicians take some more measurements and so on and so forth, and he starts asking some questions. Okay, and we're not much further beyond these questions, but he's like, well, how long would it take a fast FWD to actually fail a pavement, and how do we measure failure? You know, why don't we try a little internal test to see if we could actually do a bunch of rapid testing and fail a pavement? What type of failure would we see? Would it be deformation? Could we actually start to see cracking under a pavement? And starting to think APT. Okay, this is kind of cool. Okay, what can we do? What can we do? And you know, we're still just using the FWD the way it is. I mean, this is meant to do standard FWD testing. Haven't even gotten, what if we modified it a little bit? What if we put a different size load plate on? What if we were able to kind of move the load around, or we had some sort of robotic thing where we're not just testing the same location over and over again, but we could, you know, create wander in this or do something on a small scale pretty cheaply. So started getting some of these questions, and you know, how do distresses appear? All these things had been addressed by APT testing to some degree, but never with respect to an FWD. So we started thinking like, wow, this is kind of APT testing. So we did 3 tests. One was not really a test. Test 1 was just a shakedown of the equipment. We're trying to make sure it doesn't blow up. But that's what, you know, we observed some stuff going on with the surface of the pavement. That led to tests 2 and 3. We have a new production facility in Denmark, just outside of Copenhagen, a big warehouse, and beautiful concrete floor and everything, and they go in there with saws and they cut out the concrete floor and they put in a 5 meter by 3 meter asphalt test section. Okay, right smack in the middle of the warehouse. Oh, just broke my heart. But they go in there, they put the fast FWD down there and they just start running it. Okay, and test 2, we did 96,600 drops at various load levels throughout the testing. I don't want to get into too many details. I can't spill the beans on all this stuff because we do have a TRB paper that we're doing on this stuff. So you will be able to get the full results and everything at TRB this year or next year. Started recording permanent deformations, and we even set up control points to measure outside of the influence of the FWD, of the fast FWD testing. We did a set of 96,600 drops on the floor, and then I think, did they build a second test area?
No, they just moved over a little bit.
It just moved over a little bit. Okay. So, and then we did another test with 60,000 drops. Okay, the graphs that I'm about to show you, do not read too much into these. They look all like, whoa, wow, that's really cool. Okay, don't believe it yet. Okay, just these are very early results, and be suspicious. And you know, let's just put it this way: they're going to be challenged. Okay, Per Ulitz, we sat down. He started doing some models. He used some very simple models for measuring determining permanent deformation based off of number of load applications. Very simple models. Okay, this is what the first graph we saw. Okay, so this was a DTU model for measuring permanent deformation that he calibrated, or he made some assumptions with, and this was based off the test section. Okay, this was the shakedown test. We didn't know that much about it. We knew it was 100 millimeters of asphalt, and then it was some sort of granular material. It was done in the middle of winter. The average temperature was ranging between 0 degrees Celsius and 4 degrees Celsius. It was not a controlled experiment or anything. It's terrible. However, he does a simple little model like this. And what we're seeing on the x-axis, I didn't label the axis. The x-axis is the number of load repetitions, okay? And then permanent deformation that was measured, okay, in millimeters. So we're looking at okay, so the measured is here in red, and then we have a little simple model. okay? And this was just the DT used a very simple correlation between load repetitions and permanent deformation, okay? And the equation is up there. And let's see, we have the stiffness, the vertical strain on the subgrade, and then M sub n is number of load repetitions, yes. So again, very early, so he plots this out, he's like, interesting, okay. Then this was test one. This was the one that was not designed. We didn't know what we were getting into with this. Test two, we start doing a little bit more design. We know what asphalt section is there. We know what properties. We have some idea of what the properties of the asphalt structure are. And then we start back calculating. So as we're going through, we're doing the tests. We're taking, we're recording, of course, the deflections with the FASTF, and then we're using our software. Some of you may have used LMOD, our back calculation software. It's an Audemars Clouzon-esque method for doing the back calculation. We like using that. That's Per's brainchild. So we did that, and you can use whatever type of back calculation you want. We have the deflections. But we started looking at the modulus of the different layers. So in blue, we've got the modulus of the asphalt layer, and then the asphalt, the base layer, which is the red, and then we have the subgrade. Okay. All right. So we see the asphalt modulus is starting to decrease. All right. And then the base is kind of increasing and then steady, and then the subgrade is decreasing, steady, and then what the heck happens here? Boom, it shoots up. What's going on with that? The asphalt modulus just drops, and then the subgrade modulus increases. Like, what in the heck is going on with that? Okay. Not quite sure. We don't know exactly what's going on yet, but we think it has something to do with the fact that we had this cracking occur around the load plate, okay? That's not the load, that's the asphalt. So we're getting here. Let me zoom in on this thing. I'm glad you had me add this slide so you can actually see it. So we've got this cracking, like a shear type of crack right around the load plate. So suddenly we've got a discontinuity in the asphalt surface, okay? It makes, okay, we violated a few assumptions here. So, okay, so now we're trying to figure, okay, what's going on with this? How are we going to model this? And if you look at this, if you think about it a little bit, we're seeing this decrease in subgrade modulus, and we're seeing the increase in the subgrade modulus.
A fine grained or sandy material?
Oh, jeez. You got to ask that. Yes, and that's what we're relating that. But we think that may have been the stress hardening, because we lost the asphalt there, and then basically it's being transferred right down on that. So we're seeing that's what we think is going on. And that's actually what we tossed into the paper and to try to describe that. So yeah, I mean, we're starting to see some interesting things with this, and you know, I think I'm trying to remember, do we know what the rate of testing was? How long it took them to get the 96,000? I don't know if we put that in. It was like a couple, probably a month and a half, 2 months. Yeah, something like that. And they couldn't operate it all day round because the neighbors next to there's a condo building right next door, and it's really noisy. It's just they're not happy at all with this. But yeah, so but then we did he took the data, and on tests, I think this is from test 3. He just did another simple plot. This is correlating, again, permanent deformations back to number of load applications. And this is a CalME formula that was developed for Caltrans. Okay, so we have the asphalt permanent deformation. In green, we're looking at the permanent deformation of only the asphalt. Okay, so just one way to look at it, just remove the green. Forget about the green for a second. The model is showing in red, and the blue is the combined deformation in the asphalt layer, the base, and the subgrade. Okay, so we've got that blue is the total of all of those layers. The green is just showing the permanent deformation in the asphalt. So, you know, it's, again, this is just three little, well, two tests. One, I don't know what the first one you call that, but some initial results with this. And we're moving to kind of start experimenting a little bit more with this internally. And we're just kind of intrigued by, you know, what might we be able to do with this, and where might this be applicable, and how might this be used in a practical way out in the field. And, you know, you think about it, you put a little Kwanzaa hut over one of these things on a job. It's not that hard to envision where you might be able to use this, okay? So conclusions, I wouldn't even call them conclusions. I just say it's still kind of in an observational point with all stage with all this work. But, you know, we can apply a lot of load repetitions really quickly with this, okay? And that is typical even for APT testing. That's a pretty decent rate of load application. When you think about how many load passes you can get running an Atlas or even an HVS, you're doing this very quickly, okay? We saw it fail in permanent deformation. We're not quite sure what to make of the crack. One of the guys said that he observed a crack in here somewhere. I don't think so, but it's saying that there might be some cracking that we saw within the test area. We're seeing that the modulus values, you know, performing as you'd expect, but there are some limitations. The way that the test was set up, having that concentrated load in the same place and just beating the heck out of it, that's not very realistic. It creates some issues with the data that you're getting, so we need to maybe rethink that a little bit. But, you know, it's kind of intriguing. It's just something we didn't expect to see this. We weren't on it. We weren't looking for this. We just kind of observed this and then went down this path. So I think, you know, we're looking internally within Dynatest. We have our own R&D group. We have our consulting, our equipment, our service, and then our research and development divisions within the company. And so there's a lot of interplay amongst the consultants and the equipment group, and we all kind of make up the R&D team. But we're looking for, you know, ideas and, you know, where might this go? You know, what might be the next best? You know, what could we do with this? How could we investigate this more? And, you know, looking for insights from all you smart people who know a lot about pavements, and you know, see where this might go in the future. So I want to keep it very brief. I think we're at about 40 minutes with the presentation right now. You know, I want to open it up to questions, but I also want to get you guys out in the field so you can see this thing in action. But at this point, what do you guys think? Marshall?
How fast can you realistically accelerate this thing to? I mean, I'm talking about how many load reps we get in a minute.
We're doing, I'm doing, let's see, out at Schaumburg, I was doing 4 loads. I was doing 2 at 6,000 pounds, 1 at 9,000 pounds, 1 at 12,000 pounds. So four drops in, you know, we'll test this. You can stopwatch it out in the field when we go out there. But I think it was less than 30 seconds. It's probably like easily, if not 15, less
And
than 15
that's from start to dropping the plate to the plate being back up and the pins locked in again.
Yeah, it's fast. Yeah.
Well,
But, oh, you mean each just
you know, set it up and turn it on and let it go.
We could time it out there again.
Yeah, let's
each
time
drop is 3 seconds,
How
2
much?
seconds, 2 or 3 seconds.
No.
Yeah.
If you can get 10 drops in a minute,
Oh,
Oh,
easily.
way beyond that, yeah.
Yeah. Well, yeah.
so you're talking, you know, what? In an hour, you get 600?
At least.
We just have to be gentle to the.
And the heat is the issue right now. Yeah, we gotta keep the electronics cold. That's, you know.
Yeah.
We have a bunch of grad students blowing on.
Blowing up. Get out there.
Any other questions? Yes, sir.
So with this, it's good always to have pass, you know,
Right.
vision pattern, but try to remember that there's always Hall's interferences. So that's one point. Another thing I want to mention that this is a very good idea to use it as APT, but we cannot neglect the nature of the loading in the reality.
Absolutely.
Pulse loading.
Yep.
For me, it's like shooting a building with a rocket,
Uh-huh.
trying to design a building against
Earthquake. Yeah, exactly.
So
Yeah.
you need to understand more fundamentals of the loading, the pulse loading, and then come up with a design criteria that can be
100%
used
agree.
in design.
Yep, those are two very valid points. And, we're doing, even with moving loads, historically with the, our normal FWDs, it's a pulse load. Is that really, when you think about how a wheel is moving and what the wave, what does that deflection basin really look like? We're assuming that it's symmetric and all, there are a whole bunch, there's a lot of interesting research. That's another thing we're working on, that's top secret.
Have you done side-by-side comparison of the data, like the same location tested with?
No.
It would be good to
Yeah,
have
just-
some basis to compare with what's the old one, what's the new one.
Yep. Oh, well, we went through the.
What are things different with the FAST?
No, we did do testing, what the heck? We wrote a paper on that, or I did, the guys over in Denmark, we went through the UK correlation with it, so it passed all of that. And we did the LTPP, we were chasing, Fugro had one of our FWDs, and we were chasing them through the southeast. And the results, I think we were doing several, like side-by-side with that, and that came back perfect. So, yeah,
Same
like
deflection
same
basis?
deflections, everything. The duration of the load, the load is, I believe, not exactly the same, a little bit different. So, yeah.
Let's go check it out.
You guys want to check it out? Okay.
Oh, thank you.